know precisely the GNU base, and then you identify that with your experimental hadronic tensor WU, which you know has to appear in this object, or which this object is. And then you read off the term which is TMU. And then for that you need, of course, to see what phi and delta are. And that's the parameterization, and I already mentioned to you in the simplest way, that's just p slash plus n times a function of p. But it can be more general. Is it must be higher even?
I'm not sure.
I think the battery died.
Yeah. Can you speak?
Yes. Hello, hello.
Okay, I will change the bed.
Okay, I'll speak loud in the meantime. Okay, so that's the first part which I had here, and essentially you can do the same sort of things for other processes like the RDN, in which two hadrons come in, and then you have two times such a correlator, once for quarks and once for antiquarks. Okay, so now let's see what is the idea that we are now under talking about. So now let me get some light. This one, I think. So now I've done somehow I haven't done too much, because this is also the parton model will do this and everything. And just saying that you put one function, which is then a probability function in either this or that piece, a probability function here and a fragmentation function there. So the next step, which I already had some indications, is that all the complications which now happen in such a diagram, what I'm going to do is to tell you about those complications and how they can spoil this picture, but then how they can again be solved. And one of them is the inclusion of gluons, which will produce gauge links over here. And that's standard in the collinear treatment, but it is non-trivial in the TMD case. So that's the thing. So then you find a solution to that, and then I come with all sorts of strange gauge links I will show you then. So that's the thing. So that is in some sense improve these objects. I'll take another pen, several of them here. I improve this object, which has quarks in it, by absorbing also gluons or whatever, and it goes then into something like Taiwan 0, and then some gauge link which connects these things. So that's an improvement I'll do. And still there's the photon state. So I'm going to improve this thing by including gauge links, and then discover that this improved thing, if you still talk about these diagrams, if you want factorized form, because I assumed here factorization, I said, okay, that I cannot prove, that then sort of strange things happening, like this sign change which people are talking about with cities at the RDN and whatever. And then, okay, then you get certain nice features. And really you get even very strange features. Of course, that's a criticism that you then often hear. I haven't proven anything. I haven't proven factorization. Because then what I should do is I start from the beginning and say, oh, I have here a quark and a gluon coming and many things coming in, and all these things could be part of the nucleon. We have heard that in the previous lecture as the right source and sink operators. You can choose anything, and I mean quite a lot of operators, not only 3 quarks, but many other operators will couple to a nucleon state. So that's also here. Many other things than it's just a single quark and some remnant. I mean, it's, 2 quarks or 3 quark and gluon will all talk. But again, then I think I connect the leading one, so that's this improvement. And then still with this improved thing, if you go to TMDs, you find certain new features. And then I'll look at the consequences. As said, I criticism that is you haven't proven anything. That criticism is completely correct. But, and that's also the question, answer maybe to a question which at the end was raised, is what if, or that was raised actually in your talk, and what about if the minus sign and plus sign, this change is not seen? Yeah, then this self-consistent picture is certainly not correct. So then maybe we should have simply overlooked something and do such a process at some more detailed level where you do as azimuthal asymmetries has to be attacked in a quite different way in QCD. Maybe we forget something about that a nucleon, I don't know, has some alternative structure in it that also would affect the hard process. I don't know how, but because I think this picture with TMDs is correct, and so that at least we have a self-consistent picture. Then still it remains to be seen how to get it. But the self-consistent picture, one important thing also is that it should include is that ultimately, if given a TMD function, I must be able to give I must give you essentially say this is the operator, and then you are in business. Well, not fully because there's too much non-locality maybe in this operator, but in principle you could be in business and start cranking your operator, your computer. Okay, so that's the idea. So then let me go switch to another transparency, and let me switch to as said, I will not do all of them in order. That was not the one I wanted. Go back. So some things on how do we now get the parameterization of this object. So that's this phi. How do we get the parameterization? And let me just give you the ingredients and then give you some examples. I already mentioned yesterday this example. Here we have two functions. So what you do is you look at this object and you know that it is expressed in psi fields, states, and whatever. And what I can do is I can do parity, for instance. I can look at the object, and I can replace in this expression, in this integral, I can replace position by minus position. I know how that affects the fields, the psi fields which are in there. That's gamma zeros, you know. The parity transformed psi field is gamma zero psi. So that is what the action is on a fermion field. Now, since these objects, these phi's, were essentially used in the calculation, so they still have Dirac structure. So the I and the J, the gamma zero, the psi I goes into gamma zero, and then there's the I index, and then the K index, and then the psi K of the fermion field. So the Dirac indices are summed over, but then you see that suddenly there is a gamma zero, rather the phi ij goes into a gamma zero phi, and because of the psi bar and the psi, it's a gamma zero at the end. So that's what parity does. Then what parity does, it changes the momentum into the momentum p bar, where p bar is the space where the momentum, where the space-like component has a minus sign, the time-like component stays. So this is what parity does. And so now I'm looking at a possible form of phi and say phi could be something. It depends on the momenta of in principle it depends on the momenta of the quark. So that's the coordinates which I defined in, one of the coordinates is integrated over. That was the irrelevant one. And the others are there. But it also depends on the capital P, but then of course you have to see how all of this behaves under parity. And then it turns out that capital P slash is a perfectly allowed structure. You could say, gamma mu is allowed because this has an ij structure, this has a Dirac structure, so you could have a gamma matrix. But of course this doesn't have a mu structure, so you have to contract with something, and then you contract with either small p or capital P. But remember that small p is x times p, so capital P is sufficient. Yeah, unless the P has xp plus pt. Then also pt is a possibility. And maybe also pt times p slash. Now it turns out that having a p over here is essential, because not having a p over here is going to kill. I mean, you could have a term over here plus dot 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 without a capital P. That term, if you do this calculation, the trace of phi, gamma, delta, whatever, will turn out to be suppressed. Because P sort of is something which is large and has order Q. As soon as it is taken an inner product with something else in the hard process. If you miss this P, you miss this strong square root S or Q factor, and you get a 1 over Q. I mean, somehow the dimension will work out, but you will get a result which is proportional to mass over Q or something. So this will always give you a suppression unless there is a P. So that is what I want. And then there could be an additional P. I mean, the product of these two is essentially 2 gammas, which is still allowed. You could, 3 gammas is of course an epsilon, and so you see you have 16 gamma meters just possible. You look at all the possibilities. There's no gamma 5 allowed here, for instance, if you don't have polarization. This is a possibility without polarization, and then Berti will tell you that that a gamma 5 is forbidden. As soon as you would write down this thing for a thing with polarization, with a spin vector, then you need the gamma 5 essentially. That's what Berti will tell you. Time reversal will essentially tell you later on that one spin is not allowed. And I'll come back to that. And charge conjugation is actually usually not that relevant in this case, because it connects antiquarks to quarks. Hermeticity will tell you that the functions that appear here should be real functions, together if you use a nice real set of gamma matrices, and that sort of thing. So this is how you get your most general form. And if you only look at the first one, F1 times capital P slash, that is in essence the parton model, because P slash, or you could say X times P slash, is essentially the and P slash would be the thing you would have used if you didn't know about nucleons. So then this thing only plays the role of the probability of finding quarks. The factor of X is essentially a flux value. It comes in the calculation, in the integration.
Sorry, a simple question. For the unpolarized parts, for example, there is energy momentum conservation rule you can apply if you sum all the flavors together. Is there similar things for the transverse parts?
So what I could, so in many of these things, these correlators, as you remember, I had these 4 possibilities where you stepwise increase the integration. If you integrate over PT, you get sort of things only depending on X. If you go one step further, you get a local matrix element. If you look at this function and do the integration on the same path, F1 of X, then you do the X integration over this thing, over the full X range, and let's assume that you can measure it. That's always the problem with experimentally getting the sum rules. Then you see that the integral over X of this object happens to be a local matrix element, which is just the expectation value of psi bar gamma mu psi, and then essentially the gamma mu is the plus component, but it's essentially psi gamma psi matrix element. And psi gamma psi bar gamma psi, now everybody knows that's the probability current for quarks. And now it's local matrix element, and that expectation value, the only interpretation you can give to it, if it would be the electromagnetic charge operator, you would call that the electric charge. If you miss the E, you call it the fermion number. So that's in a natural way that the integral over X of this thing gives you the number of fermions. And then you have to do it carefully. I mean, there's psi and psi bars there. You see that it's the number of fermions minus the number of antifermions. So it is really the net fermion number is the integral over this thing. Now you say time reversal anti-quarks. Yes, this thing tells you that the anti-quark distribution, if you would say, what is now the phi bar for anti-quarks, is essentially of the same form with such a function, with a function f1 bar, and the f1 bar for positive x is equal to minus the f1 for negative x. And yeah, x, if I do an integration over all the p, d4p essentially, you would integrate over x to minus infinity to plus infinity, and then kinematics limits it to minus 1 and plus 1, and then you change the minus 1 to 0 p's into 0, 1, use charge conjugation, and that's how you get, if you do everything in detail, number of quarks minus number of antiquarks, or why in some of the experiments f1 minus f1 bar comes in, and in some of the experiments f1 plus f1 bar. Usually what comes in experiments is, if you see f1, that's, I mean, this is also written as q of x, short. This is a standard q of x, standard PDF. And then sometimes, mostly qx plus q bar x comes in f2. And the same way actually for spin. Now for spin polarized thing is that's nice. For number of quarks, that's often not that nice because q plus q bar essentially diverges for small x because there's an infinite number. But it's not a number operator, so it's not constrained. So you get all the standard collinear things which you could spend weeks on lecturing about are in here. But there's more. There's this second term. There's now things like this thing with PT slash. Now, this thing comes also in and is also allowed. And this thing has a little bit of tricky point. Later on, when I have improved these phis, and I have added a gauge link to them. A gauge link is something which runs from the point 0 to the point psi in these matrix elements. Remember, these were psi at point 0 and psi. And so you need this U. And I'll explain in a minute where it comes from which calculation. So it is also, the handbag by itself is not enough. You need all these gluons, and then they give you this. But this tells you that if you have a dependence on U, time reversal tells you that you get minus U. I mean, if something runs through plus infinity, even if it's in light cone time, the time reversed thing will run through minus infinity. So this thing is in principle a pretty useless, you would say a pretty useless thing to work with for a given gauge link, because it connects something to another gauge link. Nevertheless, it is a relation, and it tells you that if you would have a gauge link which runs through future, compared to a gauge link which is past pointing, that those two, through this relation, with a gamma, with such a gamma structure, essentially tell you that you have, if the plus gauge link and minus gauge link, that such a term would also swap sign. So, or in other words, the plus time reversal goes to minus. That's only true if here this goes to plus and also minus. For the plus it must have a plus, and for the minus it has a minus. So it swaps sign under time reversal if you want. Now the first thing was, actually this was used one time in fragmentation functions, when Collins said there is a fragmentation function that for pions that go into transversely polarized quarks. I'll tell you in a minute why these are transversely polarized quarks. So, and then it's the equivalent, now not for phi but for delta. So then it said that's time reversal. Well, then the answer, or essentially Sivers pointed out this cannot work because time reversal will forbid this. The answer is, for fragmentation functions, time reversal is not a good, you cannot even use it, because your matrix elements doesn't have completeness with xx. No, it has heteron x, and then a bra in a cat state with heteron x, ph or kx, what I said yesterday, this is not completeness. It is semi-completeness, but one particle completeness if you want. But a plane wave and something else is not a plane wave state. So you have to distinguish in and out states. And in the matrix element, these are out states. And then you can apply time reversal, that's fine, but then you get in states. And so then the left-hand side has out states for delta, and the right-hand side has in states. Now, okay, fine that the in state is not equal to the out state, but it doesn't give you a constraint. So, in the case of fragmentation functions, irrespective of gauge length or whatever, this thing is there with just a plus sign. And this is the fact that there will be, later on, no sign change for fragmentation functions, while there will be a sign change for distribution functions. The origin of these T-odd functions, because this is a T-odd function because of its behavior, the origin of T-odd functions is twofold. You can have T-odd functions if you cannot apply time reversal on the object. And so that's in the case of fragmentation functions. And you get a sign change, or you get essentially that different correlators with different gauge lengths, future and interchanged past pointing, if those are replaced, you do get a sign change, and then this is also allowed. So for distribution functions, it ultimately is also allowed to have these T-odd functions. But then the precise structure, how it pops up in a physical process, is important. And then it will turn out that the plus will pop up in semi-inclusive deep inelastic scattering, and the minus will pop up in Dralian. But the expression for the cross-section is phi put in. So that if you do a naive calculation, you would always get the same sign, but then you have forgotten this sign that the phi in Dralian is a different phi from the phi in Sidis. The one is phi plus and the other is phi minus. But the functional dependence is the same, except for this minus sign. So it's, I hope, a little bit clear what this sign change really means. It means that you have matrix elements that are related, that do change sign at some point, and then of course the important part is that you still have to prove is that phi plus appears as the right correlator in a handbag for semi-inclusive deep inelastic scattering, and that phi minus is the thing which appears in a handbag calculation for Dralian. But that's a rather trivial calculation. Okay, now let me now again swap to something else. Oh no, that is actually the next thing. So you can also include not only this, the momentum, but also the spin. And I promised that I would tell you what the spin was, what this spin vector is. Because people put in spin equals 0, isn't it? So then you say, oh, put in spin equals 0, then these terms are not there. But so what you see first of all is you not only get f1, you also get another function and yet another function. You get 3 functions now because you have spin. Of course you have a dependence on s, and of course s will come in. And now it depends, of course, how you write s. Now I write s is simply a vector, a 4 vector. I write it in terms of the momentum. Then of course this looks very much like helicity. Yeah. Forget about this term because it's proportional to m, so it doesn't matter anyway. But you need it. You need also the component along n. And then there's a transverse piece. And these two pieces are related. They both go with SL because otherwise it doesn't satisfy the requirements of a spin vector. What did you learn in high school? S dot p is equal to 0. A spin vector is orthogonal to the momentum, and s squared is minus 1. Did you? But rather than this, you have learned you may have learned something else about spin. What do you do with spin degrees of freedom? You essentially in a cross section, what you do is you say, oh, if I have spin, I would do 1 over 2s plus 1 sum over the spin degrees, if let me call them alpha. That's what you do for initial states. So if you have initial states, which is the alpha and then the matrix element and then beta. So beta is the final state, and I have to sum over this m alpha. So alpha matrix element, so scattering matrix, beta is the amplitude. I have to square this. And so what do you do with spin? In the case of an unpolarized target, you do 1 over 2s plus 1, sum over alpha, isn't it? And what do you do with the final state, beta? You simply sum over beta also. This would be a spin average cross section. You sum over the final state spins, and you average the initial state spins. So what is the spin vector? Now in this case, you would say sum 1 over 2s plus 1 sum over the spin states. That's what's called unpolarized scattering. So you expect the result at s equals 0. So why is s equals 0? And if you have a fully polarized state along the z direction, you would pick 1, and everybody would tell me, then I have to take s probably along 1 and probably along the spin direction. That's correct. But what is happening halfway? If I have 50% of the time or a polarized thing and or 75% spin up and 25% spin down. People know how you do this? Density matrix? Yeah, you do a density matrix. So usually when you not have this thing, but you have, let me see if another red is ready. If you have this thing, you would say, I do a sum over alpha, and I do essentially some probability alpha rather than having this, and then I have this alpha m beta. Let me not care what I do with beta, m star or m dagger if you want. M dagger is I think the correct thing. And then beta m alpha. So I have this. So this is usually done is the following way. This you say this is a trace of, and then I'm going to take beta m, and then I put here a density matrix rho for the initial state, and then I put m dagger beta. So this is what the cross section is proportional to, and then rho of I, the initial state, is nothing else than a sum over alpha, probability alpha, alpha, alpha. And this is what is called a density matrix. Yeah? And maybe you also learned, and I'm not going to explain that in all steps, that if you have a spin 1/2 particle, that this thing can be written as, now for the unpolarized case, what is it? Oh, then it's the unit matrix. And that's indeed what it is. It's 1/2 times the unit matrix, the 2×2 unit matrix, plus, and now what else can it be? Okay, look at this thing, it's Hermitian, so it must be multiple, and it must be built up from the sigma matrices. So it is plus sigma dot s. And s is then called a spin vector. That's the spin vector. And it's that vector that is essentially appearing here and that you parameterize. Now you say, yeah, this is a 3 vector. I multiplied it with the spin. Now this is because this is all done for static spins. This is, for instance, in the rest frame of a spin 1/2 object. Now nevertheless, in the rest frame, it's a space-like, a purely space-like vector. So in the rest frame, as I can make it into a form vector, which in the rest frame is of this form, and then in any other moving frame, it's of a different form. Then it picks up 0 components. And that's why you can write it like it is. Because the covariant way of writing a spin vector then is, it is a spatial vector, but it has to be in such a way that in the rest frame it's purely spatial. So it must be dotted into the momentum, it must be 0. And this thing must be essentially, actually this is not correct. The correct thing is that the length is, in absolute value, is smaller or equal to +1. It's negative because it's space-like, but it must have length less or equal to 1. If you put this thing not in it, you have the unpolarized case. If you put this thing in with length 1,